Well, greetings everybody. What you're looking at here is a screenshot from a problem on MyMathLab, and you'll find a similar problem on your assignment. And this would be a difficult problem to solve if you'd never seen anything like it, okay? Of course, some people could solve it without being taught. Some people are really good at math, but I think the average person in class would need to see an example. So I'm going to show you how to solve this, and then I want you to just apply what I show you to the problem that you find on the assignment that's like this one. Okay, so I hope that that makes it as straightforward as possible, but it's still, I think, a difficult problem. Okay, now I will explain a lot of what I'm doing here, and if you're just solving it, you might not think about it in that much detail, but just as a teacher, as an instructor, yeah, I just feel it'd be wrong if I didn't explain, as much as is as reasonable in a short video about why I'm doing what I'm doing. Okay, so you take away from this video what you want and need to solve the problem that you find in the assignment. Okay, I might be telling you a little bit more than you need or want to hear, but that's the way it goes. All right, the question's like this. It says that we're going to release a homing pigeon. So say its home is at this point L, and we release it out over a body of water at this point B. Okay, so it will fly to the shoreline, and then it will fly, it wants to take the shortest path it can, let's say, back to its home at point L. So point P is this point it flies to on the shoreline, and we don't know where that point is. It's just somewhere along the shoreline right here. And then this point L is where it flies to from there to get home. Homing pigeons want to find their home, okay? And it says that the boat's 8 miles directly out from the shore, and this point and this point are 16 miles apart, and so on, okay? So I did a little bit of relabeling with this. I wanted to draw my own picture, and I'd say, well, there's this boat out here, and the pigeon's going to fly towards the shore, and then it's going to fly along the shore to its home. Now, I need some more variables, okay? Once you get past arithmetic, when you're doing math, when you go to algebra and calculus, then you have variables, you have unknown numbers. Like, I don't know this side of this triangle that was given in the picture, so I might call it X. And I don't know this little distance here from the shoreline where the pigeon flies to the home either, so I might call it Y, you see? So that's what we end up having to do in algebra and calculus and the higher math. Now, let's do this. I need to track the path of the pigeon. It flies from the boat to the shoreline to home. So I need to know, or at least give a label to what this distance is right here. This might be 8 miles, but how far is this? Because this is actually the path the pigeon flies on, okay? So for that, this is a right triangle, okay? And there's this law that governs all right triangles that there ever could be in the universe. And let's say we have a right triangle. That means that this angle is 90 degrees, or what you might call a corner. Okay, and we'll say if this side's A and this side's B, then this side across from that right angle is the square root of this side squared plus this side squared. So in general, we say square root of A squared plus B squared. So that's what I could use to get this side right here. It's the square root of 8 squared, which is 64, plus x squared. Okay, so now I have an expression at least for the distance from the boat to the shoreline. What about from the shoreline to home? Well, so I called this x and I called this y, but it was given to me in the problem that it's 16 miles from here all the way to here. That means if you take x and you add y, you get 16. But in order not to have too many variables, we need variables, but I don't want to have x and y if I can just use x. I could say, well, if x plus y is 16, then y is 16 minus x. So this side right here is 16 minus x. So it flies along this side, whose distance is root 64 plus x squared. Then it flies this way, which the distance is 16 minus x. Okay, so that's my update on the picture that was given in the problem. Now, from there, it tells me something else, okay? Birds take energy to fly. I mean, just like if you're walking or running, that takes a certain amount of energy. So it tells me this fact, and this surprised me when I read it for the first time. It says, a pigeon needs 4/3 as much energy per mile to fly over water as over land. And I never heard that before. I just didn't know. So I went and I searched on the internet. Is it more difficult for birds to fly over water? And it says it's more difficult to fly over water than land. I mean, that's at least what I found when I searched. And you can read a little bit more about that, but apparently that's true. So 4/3, that's like it takes 1.3 times as much energy to fly over water as over land. Okay, now I say all that just to kind of get acquainted with the information that we have and so on. The question is this, okay? Find the location of this point on the shoreline that will minimize the energy that the bird uses to fly from the boat to the shoreline to home, okay? So what I want to do is minimize the total energy used to fly from the boat to home. Now, I've got to get this energy used to fly worked into this. So here's the way I did it when I solved it. I said, suppose E is the energy per mile the pigeon uses to fly over land. And if that's the case, if that's what I call capital E right there, then 4/3 times that is the energy used per mile to fly over water, okay? If I have those and I have these distances, then I can get you a function t that is the total energy used to fly from the boat to home. And that's what we want to minimize. When we minimize that, we'll find this point on the shoreline that takes the least effort for the pigeon to fly back to home, okay? Assuming it flies in a straight line to the shore and a straight line to home. Okay, now, all right, how would I do that? I'll notice this about it. This thing, root 64 plus x squared, that's the distance in miles from the boat to the shoreline, okay? And these numbers, E and 4/3 E, that's the energy per mile that the pigeon uses to fly over either land or water. What do you get when you take a number that's energy per mile and multiply it times a distance in miles? Well, the miles cancel and you get energy. So if I take 4/3 E, the energy per mile used to fly over water, and I multiply it by this, root 64 plus x squared, the distance in miles that the pigeon flies over water, then I get this, 4/3 E times root 64 plus x squared. That number will be the energy used to fly over the water. Plus, okay, if I take E, the energy per mile the pigeon uses to fly over land, times 16 minus x, the distance in miles from the shoreline to home, then I get the energy used to fly over land. Now, if I add those together, what's that? That's the total energy that the pigeon uses to fly from the boat to the shore to home. And that's what we want to minimize. Okay, so if I have a function that tells me the total energy used to fly from the boat to the shore to the home, how would I find its minimum? Because the question was, what's the minimum, like where is this point right there that minimizes the energy used? So like how do I find the minimum of this function t? Okay, well, one thing that we've been learning is that if you have any function and if you find its derivative and you solve it for 0, you'll get the minimum or maximum, whichever one you're looking for. In this case, we're looking for the minimum. So I rewrote t. I rewrote the root as an exponent of 1/2. And then what you're looking at here is me using the rules for derivatives to find t prime, okay? So 4/3 e. E is a constant, okay? However much energy per mile the pigeon uses and so on, that's a constant, that's a fixed number. It wasn't given to me in the question, but it's still a constant. And in calculus, we treat constants and variables different. That's why it's important to know it's a constant. Like if y is 2 to the third power, what's y prime? It's 0 because 2 to the third power is a constant. It's 8. The derivative of any constant is 0. What if y was x to the third power? Well, and then now x is a variable. The rule for derivatives that applies to a variable in this case is that y prime is 3x squared. So it's important to know when we're doing calculus what's a constant, what's a variable. And e is a constant. So when I take the derivative of this, t to t prime, I'm going to treat that e like it's a constant. So I carry down the 4/3, I carry down the e. The 1/2 comes to the front, I take away 1. 1/2 minus 1 is negative 1/2. The derivative of that inside part is 2x. That's the chain rule. Plus, carry down the e. Derivative of 16 minus x is negative 1. So that's how I get the derivative. Canceling the 2's and otherwise combining the terms, I get that. Now, there's your derivative, okay? I can go into more detail about that if needed, but it's something we've covered already, and so I didn't want to make it too much the focus of the video. So if I solve t prime equals 0, I'll find that minimum value. So here you're looking at that equation. Here's what I did. I factored out e like that, and then I divided both sides of this equation by e because I noticed I could just get rid of it and it'd be better to get rid of it. What if you divide the left hand side by e? You'll cancel the e. And what about the right? What's 0 divided by e? What's 0 divided by any other number? It's just 0. After that, I added 1 to both sides to get like that. Then I cross multiplied to get this. From there, I got this root. I need some way to deal with that, get rid of it. So I square both sides. So I get 4x squared is 16x squared. 3 squared, 9. And then I squared both sides just to cancel that root. That's the only reason I did it. Root 64x squared, 64 plus x squared is 64 plus x squared. So now I don't have that root to worry about. I distribute the 9 in there. I get 576 plus 9x squared. I move the 9 over. I get 7x squared is 576. I divide by 7. And then to solve that square, I take the square root of this number. Okay, so square root of 576 is 24. And square root of 7 is just the square root of 7. So that point P up here, that should be 24 over root 7 miles away from this point. Okay. All right. So 24 over root 7. If that's the exact answer. If you rounded it, you get 9.0. So it's about 9 miles from where the boat is along the shore. Okay. All right. Now, as far as the answer goes, look at it up here. It says 24 root 7 over 7. That's kind of like my answer. The answer I got was 24 over root 7. That will work too. What's done here is something called rationalizing, and I just don't think it's important for our class. So when you get to this point, you'll get like a number over root something. Just enter it that way and it will work just fine. If it doesn't, if you feel like you're getting it right and MyMathLab keeps rejecting it, then go ahead and just contact me and I'll have a look at it. Okay. Now that's the exact answer. If it happened to say to round it, then I might round it to however many decimal places it says, and it'll be like 9 point something in my case. All right. Okay. So now that's a big problem. There are lots of details. Like I was saying, it would be difficult for somebody to figure this out if they'd never seen anything like it. But hopefully I showed you the steps enough that you can recreate them and solve it for yourself.